This is on-off valve. I'm going to turn it on. You'll hear the water noise. There's a filter. There's a different kind, a one-of-a-kind coil for the music team. It has an on-off valve, which is turned down a little bit. And here's how the water goes into the coil, out of the coil. There's some back pressure. There's actually a sprinkler head that's forced open, and they're adjusted different ways to provide some back pressure. Water goes into a drain tile to reduce erosion, take away the energy. Now here's some of the regular coils. It's covered with a screen to protect it. It has an on-off valve, and part of that is so we can have a port to blow air through it. Another port, you take that cap off, we can put antifreeze in there, and with the smaller port unplugged, when it starts running out the lower port, we know that it's full of antifreeze. We do this after we've blown out the air. That's a typical coil. I'll show you one more. Also want to show you a window that doesn't have a coil. This one's shut. It pivots open from the top. The top will slide down a few inches. This one has a board over that part. We are going to cover all of that up. So you see in the end of the coil, it also has a similar setup for the water to go in, out, the drain tile. Still some things to pick up. The duct tape's going to go away. We'll caulk it in. And then where these channels are, we're going to put plexiglass that will protect the coils summer and winter, even when the window's shut. Right now the window's protecting the coil, it's open. However, we want to be able to open or close the windows, and this plexiglass in the channels will seal the air so that window open, window closed, even air in between, the air going into the sanctuary will have to go through the coil. Okay, now just look at a couple more. Again, here's one window that doesn't have a coil, may never. And here's another setup, slightly different, on-off valve in, or we'll pour the antifreeze in here, and we can put air in. And we can use these valves to dial down the flow if we want to rebalance which window. This is the smallest coil in the back window. It was the first one we got. Has the brass fitting right now, which I may move to a better location. We can use that for putting air in to blow it out, and then of course the air goes out to drain, or the water goes out. By using these valves, we can make sure the compressor only has to deal with one coil at a time. You can see perhaps 3 sprinklers just kind of trickling in the garden right now. And what's going on is they were going great guns until I turned on the cooling. And I'm going to turn these sprinklers off so that all the water can go to the cooling. Earlier we didn't have any back pressure on the cooling system. Here's the shut-off valve. Now it's off, sprinklers are off. So, and without the back pressure, the pump might have not sealed properly. I think we're getting more GPM with the back pressure than we had without. Okay, the water's been running a short time. We're looking at a coil from the inside. This is actually the window open. It seals off between the bricks in this case, and the coil down below. And if you can see this, we can get some measurement of airflow. In this case, it's air velocity in feet per minute, and we can multiply that by the square feet of the coil, if each coil being different, to get the cubic feet per minute through each coil, and add them up to get the total cubic feet per minute. I'll show you a spreadsheet later. This also reads out temperature. It says 80 right now. I hope it drops down. And now there's another device. This gives us some sense of the temperature of the coil, the water in the coil. And right now, even though the well water should be below 60, we haven't cooled down the pipes and the coil and all that much. We're at between, it varies across the coil, 68 on that side, 71 on this side for that particular coil, and so on. So we can get some temperature information, we can get the flow rate. This is the largest coil. It's a 16-inch. I actually had to make it a little narrower by about an 1/8 inch to squeeze it between the bricks, so it's a tight fit. 70 on that side. This one, for some reason, sometimes runs a little warmer in the middle, but right now it's 63 on the left side, 65, 66, 67. There's some variation up and down too. 69 at the top right now. This one's not varying up and down, but it depends on the wind, the airflow, a lot of things. So as you can see, it's coming down. We're at 61 in this corner now. And then the front coil is the second largest. It's a 15-inch, but is longer than the other. 63, 62, 63, 64. Varies a little, but at least we're in the low 60s on the coil temperature, and that'll start bringing the water temperature down. Now I'll show you the vent, and it's reading like 63. This is the music team vent. 69, 67, 63. This is an automotive part. I don't know how well it'll last. You can see there's a cheap thermometer up here I use to monitor things. Right now it's saying a little under about 70. Now what I do to measure the air temperature in the room, in part I can use the meter that does airflow and temperature, and I can also measure the air temperature going out of the duct. It says 80. The wall is about the same. Sometimes a good sign will be if the wall is warmer. Now if you check the ceiling, 85, 88. That's the sun side, and this is the not sun side. This is the north side. That's 86. So there's a difference. Now the next bit I will put up a spreadsheet, show you how these numbers can help us optimize the system. Quick walkthrough on the spreadsheet. We'll zoom in for part of this right now and show you, for instance, here are just some standard values so that they go into the equations. This whole bunch of things I copied off the internet, out of textbooks, whatever was needed. Okay. So, we start with the calculations. Now let's work our way up. Right at the top, let me show you what we have here. What we have is calculations. We know the size of the sanctuary. We calculate the cubic feet of the sanctuary volume. We have a standard number of BTUs per degree per cubic feet of air. We're going to need that. Then we have BTUs per degree per gallon of water. So then we have a slider. I'll exercise that for you, show you with the arrow. So I can move the slider if, for instance, if the attic fan can move 1,000 CFM, then we can have a certain number of air changes per minute, and about 1.6 per hour. For one change, 13 minutes. I guess that's then, so 4 point something changes per hour. The outdoor temperature is 85. If the water starting temp is 70, then certain things happen. And then if you continuously lower the air to 77 degrees, for example, and the 4 windows have a velocity together with this many square inches, that amounts to 6.85 feet per second. Okay, and the air delta T, a change in temperature, will be about 8 degrees. Okay, so the air BTU reduction, we calculate the water delta T. Let me scroll that. And then we get to gallons per minute. Let me move this, zoom out so you can see a little bit more. Okay, I'm going to move the top slider and watch the highlighted yellow, required gallons per minute. This is where the power is. You can figure out what you can change to get the most bang for the buck. You see as I move the slider that this number here changes. So as I change that, if I only have 10 GPM, I need to keep dropping this down. If we move too much air, the water won't be able to cool the air enough. And if the outdoor temperature is 85, we can change it, and of course the higher that is to get the temperature we want, the more water we have to flow. And the same thing, if the water temperature starts at 70, that's one thing, but if it starts at 55, you can see that the GPM required of water drops a lot. Okay, so the power is in then using the spreadsheet once we've measured some data. And this is, if we decide we don't need to cool below 80 instead of 77, then of course that changes the GPM required. So these are all the trade-offs.